For a certain chemical reaction, delta H is negative 35.4 kilojoules, and delta S is negative 85.5 joules per Kelvin. A, is this reaction exothermic or endothermic? Well, it's exothermic. Does the reaction lead to an increase or decrease? Does the reaction lead to an increase or decrease in the randomness or disorder of the system? It's got a negative value for delta S, so it leads to a decrease in disorder. And C, calculate delta G naught at 298 Kelvin. All right, so we're plugging into this relationship between delta H and delta S for C. Now, this is the problem or the trick with this problem. Delta S is given in joules per Kelvin. Delta H is given in kilojoules. What you want to do is convert delta S into kilojoules. So this way you can plug it in. They have to be in the same unit. So delta H is in kilojoules. Delta S is in kilojoules per Kelvin. When I multiply by Kelvin, that'll cancel Kelvin, and I'll end up subtracting this term from this term in order to get the change in kilojoules. So in the end, we have a negative 9.92 kilojoules for delta G naught. This means this is a spontaneous reaction, one with a large K value. Using the data in Appendix C, calculate delta H, delta S, delta G at 298 Kelvin for each of the following reactions. In each case, show that delta G is equal to delta H minus T delta S. So we can look up on the table what the delta H's of formation for the reactants and the products are. Elements, of course, are 0. So we look up what the delta F of formation of hydrogen fluoride is, multiplied by 2, and that's the delta H, or the enthalpy change in kilojoules. We can look up S's of formation, right? These are absolute values. We subtract the S's of the products from the S's of the reactants to get the change in delta S at standard conditions. Calculated the same way, right? The sum of the products minus the sum of the reactants. I get this in joules per Kelvin. And I can do the same for delta G. If you look at Appendix C, you have delta G naught values. So you can plug it into products minus reactants, get the change. Notice delta G naught for the elements is 0, just like delta H is. All right, so if I'm going to use delta G is equal to delta H minus T delta S, I've got to first convert delta S into kilojoules per Kelvin, and then I can plug into the equation. And it should come out the same. You should get the same value for delta G naught using delta G naught is equal to delta H minus T delta S naught as you would products minus reactants. Do the same thing for B. Look up what the delta G's and the delta H's and the S's of formation are for the reactants and the products. If I'm going to use delta G is equal to negative T delta S, I've got to first convert delta S into kilojoules per Kelvin that I can plug into the equation. Negative times a negative makes a positive, so when I add this to the negative value for delta G naught, it makes the value for delta H less negative. Nonetheless, it doesn't make delta G negative, right? So we still have a negative delta G naught value, and this means the reaction is spontaneous. Using the data from Appendix C, calculate the delta G naught value for the reactions. Indicate whether the reaction is spontaneous at 298 Kelvin under standard conditions. All right, so we've already established that if you have a negative value for delta G naught, you're going to have a spontaneous reaction. So I just plug into products minus reactants, right? If I completely change reactants into products, I look at the value for the complete transference, and it's a way of equating it to the equilibrium constant. Plug into products minus reactants. If I get a positive value, it's a non-spontaneous reaction. Plug into products minus reactants, just like with delta H, the delta G values at standard conditions are 0 for elements. I get a positive value for delta G naught, I have a non-spontaneous reaction. Consider the reaction where nitrogen dioxide turns into dinitrogen tetroxide. Using the data from Appendix C, calculate delta G at standard conditions, calculate G at non-standard conditions if the partial pressures for NO2 and dinitrogen tetroxide are 0.4 atmospheres and 1.6 atmospheres respectively. All right, so when I go to Appendix C, look up the delta G's of formations for the products, delta G's of formation for the reactants, plug them in and solve for delta G, I see this is a spontaneous reaction. Now, the question is it spontaneous with these pressures? Am I still going forward? Am I at equilibrium with these pressures, or am I past equilibrium? So I plug into the relationship between G at non-standard conditions and G at standard conditions, plus RT, natural log of Q. Q is reactants over products raised their stoichiometric coefficients. So I take the given pressures for the products, 1.6, and the pressure for the reactants, 0.4, plug them into Q, and solve for delta G absolute. What this positive value tells me is that I've gone past equilibrium. I've had to put energy in to go past the point where the reaction stopped. So this is reaction, if it's going to get to equilibrium, it's got to slide backwards. You have too many products here. So this is how you use the relationship between G absolute and G naught. Predict the position of equilibrium. Use the data from Appendix C to calculate the equilibrium constant K at 298 Kelvin for each of the following reactions. Hydrogen reacting with iodine to form hydrogen iodide. Okay, so we look at Appendix C, we look up the delta H formation of the products, we sum up the delta H formation of the reactants, and we subtract to get delta G at standard conditions. And we set that equal to the equilibrium constant, all right? Negative value for delta G naught. My expectation is I'm going to have a very large K value, right? This implies a spontaneous reaction. So I rearrange and solve for K. R is the gas constant. The temperature is 298. I divide into the negative value for delta G. So a negative times a negative is a positive. Take both sides to the base E and get a large K value, right? So a release of free energy at standard conditions applies a spontaneous reaction. B, again, we go to Appendix C and we look up the delta H of formation of the products. We sum those up and subtract the delta H of reaction the delta G of reaction for the reactants. Get the change. We have a positive value for delta G. So the expectation is I got to put free energy in to make this happen at standard conditions. I'm going to have a small K value. Small K value. The Ka value for nitrous acid is given in Appendix D. Write the equation for the chemical equilibrium that corresponds to a Ka. All right, Ka represents the ionization of a weak acid. B, by using the Ka, calculate the delta G at standard conditions for the dissociation of nitrous acid. So we're just working backwards, right? We're plugging into this equation. In this case, though, we're solving for G naught. So you look up the Ka value for nitrous acid. It's non-spontaneous, so I expect a positive value for G naught at standard conditions. C, what is the G at equilibrium? G at non-standard conditions at equilibrium is going to be 0, right? That's what represents being at equilibrium. So that's that. D, what is the value of G at non-standard conditions if I have these concentrations? So again, we're using this relationship between G naught and G and the reaction quotient to solve for, in this case, what the free energy value is. So we plug the concentrations of the reactants and the products into the law of mass action. Take the natural log of that value, multiply it by RT, and then add it to that delta G naught value to get G. All right, having a negative value for delta G means with these concentrations that were given, I'm not at equilibrium. I'm still going towards equilibrium. Still making products, still losing reactants.